We begin our analysis with the classical model for particulate description. It has got two famous names attached to it. James Clerk Maxwell was perhaps the greatest physicist, mathematician of the 19th century. In many ways, you can think of Maxwell as the connector between Newton on the one hand and Einstein on the other. Maxwell is perhaps most famously remembered for being the father of electromagnetic theory in his epochal publication in 1873 of the way electromagnetic forces interacted. These are now called Maxwell's equations. But Maxwell had wide other interests as well. In particular, he contributed to this classical theory of how particles were distributed. Maxwell also was a dilettante in many other areas. He famously was the first person to examine the rings of Saturn and conclude that the rings must be made up of many, many, many tiny bodies and were not just solid rings. He was also a poet, and he published famously in Victorian light verse, but we digress. His collaborator in these ideas was very different in personality from Maxwell. This was Ludwig Boltzmann. He's famously attached to the idea of an articulation of the statistical nature of the second law of thermodynamics, that disorder, entropy increases. Boltzmann, towards the end of the 19th century, pushed an atomic view of physics. This was not popular at that time. But the ideas he was proposing, like Maxwell, proposed a statistical distribution of atoms to explain physical phenomena. Boltzmann sadly took his own life in 1906. He was an intense man, suffered bouts of depression, and sadly, he died just a few years before his theories were dramatically confirmed in experiments done by J.B. Perrin in Paris to measure Avogadro's number. But the main thrust of the Maxwell-Boltzmann ideas was essentially combinatorial. And so here's the setting. Recall, we have a setting where we have n balls. In this case, I have shown you 12 balls. And our urns, for definiteness, let us consider 4 urns. And now I've dispensed with the idea of a physical urn as an object which can receive balls. Again, from a purely metaphorical point of view, all that matters are these objects which are called balls, which I'm going to distribute into these receptacles that I shall call urns. So now I have 12 balls and 4 urns. Now, suppose one is interested in a particular occupancy configuration. In our notation, 4, 2, 0, 6. Now, what does this mean? It means we are looking for distributions of these balls into these urns in such a fashion that the first urn collects 4 balls, the second urn collects 2 balls, the third urn is empty, and the fourth urn contains the remaining balls, 6 in number. Okay, here's an occupancy configuration. In how many ways can this be done? Okay, let's pause for a moment and think about this. In a setting like this, it is convenient to begin by asking, what is the first step in the process? And the first step is, well, we want to distribute 4 balls into the first urn. Let's go ahead and do this. Now, here is a particular distribution of 4 balls into the first urn. But this could assuredly be done in many, many different ways. How many ways? Well, there are 12 balls, and you're going to choose any 4. So there are 12, choose 4 ways of distributing 4 balls into the first urn. With the 4 balls in the first urn, we now turn attention to the occupancy of the second urn. 2 balls have to go there, but 4 balls have already been removed from the pool. So we have 12 minus 4, or 8 balls left. Of those, 2 go into the second urn. How many ways can this be done? Well, 8 choose 2 ways. Or, in a more clear way, 12 minus 4 choose 2 ways. Excellent. Now, at this point, we've removed 6 balls from the population. We have 12 minus 6 balls left, or 6 balls left. Of those, none go into the third urn. Of course, there's only one way to do this. Nothing goes in there. But to identify this logically, what we're saying is that we have 12 minus 6, or 6 balls, and none go into the third urn. This can be done in 6 choose 0 ways. And now we come to the last urn. At this point, we have 6 balls residual, and all of them go into that last urn. This can be done, of course, in only one way, or spelling it out in 6 choose 6 ways, which is exactly 1. Good. And now we observe we've got this flock, a covey of binomial coefficients fluttering onto the screen. And the moment you write this down, oh, well, it does look formidable, doesn't it? But of course, naturally, we will want to try to simplify this. And so we begin by writing down explicitly what each of these binomial coefficients really is. Pause and do this. Good. Now you've written down what these binomial coefficients mean, and now we've got a long string of ratios of factorials. It does look intimidating. But pause, take a good look at what you've written down. Do you see any patterns? Of course you do. You realize that terms cancel in numerator and denominator. An 8 factorial cancels in numerator and denominator, and 2 pairs of 6 factorials also cancel, which means the expression simplifies. Recall that 0 factorial is 1, so the last 0 factorial I'm going to replace by 1. And now I've got an expression which is still large, but it clarifies. The expression has the factorial of the number of balls in the numerator, and in the denominator, a product of the factorials of the occupancy numbers. It couldn't get much simpler, could it? Now that we've built up a right understanding of a simple implementation of the schema, let's promptly generalize and come up with what an expression should be in the abstract setting, where we have n balls and r urns. And the process will be exactly as we saw in this example. If we start with n balls, of those, k1 go into the first urn. How many ways can this be done? Of course, n choose k1 ways. The moment k1 balls have been placed in the first urn, now there are n minus k1 balls remaining. Of those, k2 have to go to the second urn. And this can be done in n minus k1 choose k2 ways. At this point, we have n minus k1 minus k2 balls left. Of those, k3 have to go to the third urn, and proceeding in this fashion. By the time we get to the last urn, from the number of balls, we've taken away the sum of the first r minus 1 occupancy numbers. Of course, if you think about it, you'll realize this just means you have k sub r balls left, and they all have to go to the last urn. This can be done exactly in one way, which is that last big binomial coefficient on the screen. Well, we have a long expression. The next step, of course, is to try to simplify it. So we write down explicitly what each of these binomial coefficients is. Pause and write them down. As before, you observe that factorials cancel one after the other in numerator and denominator, and the entire expression simplifies beautifully again. 2, 1, where you have a ratio, the factorial of the number of balls in the numerator, and in the denominator, a product of the factorial of the occupancy numbers. It couldn't get much simpler. Here now is the expression for the number of different ways in which a distribution of n balls into R urns could engender a given occupancy configuration K1 through Kr. The question, of course, now is, how many ways can I distribute the balls in the urns in the first place? Oh, but this is easy. If I think of arranging the balls from left to right, ball 1, ball 2, ball 3, ball 12, ball n, and identify which urn each ball went into, then we have one particular distribution of the balls into the urns. But this means that we have an ordered sample of size n selected from the urns where the sampling is with replacement. Multiple balls can occupy an urn. Of course, we know the answer to this. It is inevitably r to the power n. And now we've got a complete story. Okay, and this is the classical model for the distribution of balls into urns, classical particles into states. And these lead to what are now called the Maxwell-Boltzmann statistics, named after James Clerk Maxwell and Ludwig Boltzmann. The chances that in a random deployment of n balls into R urns, the probability that a particular occupancy configuration K1 through Kr is seen is given by the ratio of the number of ways in which this occupancy configuration could be realized divided by the total number of ways of distributing balls into the urns. Of course, bear in mind here that these occupancy numbers must be non-negative and they must add to the total number of particles in the system. Now this looks beautiful, elegant, and a complete story of how particles in nature might distribute across states. There is just one small fly in the ointment, and it is this. Investigations in the early part of the 20th century showed that there are known physical particles which satisfy this completely natural distribution. Let me repeat that again. There are no known physical particles which obey this completely natural physical distribution. This is remarkable. The probabilist William Feller wryly remarked that apparently particles in nature do not come equipped with human common sense. What could have gone wrong? The model is so palpably correct. I mean, you take a bunch of particles, you throw them out, and they distribute randomly. And the count is inevitably given by the Maxwell-Boltzmann formula on your screen. Why on earth do particles not obey this completely obviously correct description? This points out the perils in applying clean ideas which appear to have a logical immediacy, a correctness, and making the leap to believing that nature must in fact conform to our idea of mathematical cleanliness. In this case, nature at the quantum particulate level apparently does not like this way of common sense. And by the early part of the 20th century, it became clear that this classical idea was shipping water. It could not hold as a description of reality that was being observed. Something new had to take its place. This will be the content of our next sliver. Right. I should not let you go, however, by imagining that this idea of Maxwell-Boltzmann should just be immediately confined to the nearest trash can. These ideas had enormous impact. And in the realm of the description of a macroscopic view of gases of the world, they have enormous accuracy. Where this kind of description falters is at the individual quantum mechanical particulate level, there particles behave in strange and wondrous ways. And we shall come to that next.